So what I'm going to do is I'm going to use a spreadsheet app here, just to kind of try and organize things a little bit more. And so I'm going to, narrow all these columns so that we can kind of use them for individual bits. And I'm going to have to flip around so I can see the screen because the screen mirroring is not working still. So this will be a little awkward, but we'll manage. Okay, so let me just take a bunch of these cells and just narrow them here. So we've got some spots. Okay, so the topic I want to start to talk about today is, so last time we talked about how do you represent integers, unsigned integers, so meaning 0 and positives only. How do we represent those in binary? And we did it in 8 bits just for sake of demonstration, but you can of course do this with more bits. Okay, and the two lessons we learned there is that the arithmetic system works mostly the same as arithmetic that you've been doing since grade school, with one exception, right? What happens when you get to the top, so to speak? Well, like, okay, so like, let's say we had 200 plus 60 last time. Okay, what's 200 plus 60? 260. What about if we're only working in 8 bits? What would the answer be? It would actually be 5, or 4, sorry. Because what's the largest number that you can encode in 8 bits? 255, okay. So it would roll over and you'd hit 255 and then you'd be like, okay, well, I need to do, however many more. So I 255, 0, 1, 2, 3, 4. And that's why you get 4, okay? So what is this arithmetic like? Like what's the analog for this arithmetic that you've all been using your entire life? Clocks, right? This is clock style arithmetic where it wraps back around, okay? Okay, so if you do this with more bits, you still have the same problem. It's just that the maximum number is a lot bigger and might be big enough that you never really have to worry about this. Okay, so what we're going to talk about today is how do you do this with signed numbers, meaning that you want to be able to encode both pluses and minuses. Okay, and so I'll tell you a little story to start off. Well, first off, let's say that you have a 32 bits. What's the biggest number that you can encode with, or how many numbers? Let me start there. How many numbers can you encode with 32 bits? It's a lot, but how am I going to calculate this? Like, so I don't care what the actual number is, but like, what would I use to calculate this number? So how did I get 256 out of 8 bits? Okay, so if I have 8 bits, how does that get me 256 things? Huh? Not quite. It's a power of 2. So what's 2 to the power of 8? Okay, so it's 2 times 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 2. What is that? 256. Okay, so that's where we got it. And the reason, right, is think of just this the exact same way that you would if I asked you, well, how many different possible arrangements are there if you flip 8 coins? Well, if you flip 1 coin, how many arrangements are there? If you flip 2 coins, how many? If you flip 3 coins, how many? 4, and so on, right? So each time you do this, you're multiplying by another power of 2. Okay, so 8 bits means 2 to the 8th things, patterns can be encoded, and 2 to the 8th is 256. Okay, does that make sense? All right, so what about if I were to do this with 32 bits? Yeah, right. So it's whatever 2 to the 32nd is, okay, which happens to be 4 billion, blah, blah, blah. Okay, whatever. That seems like a pretty big number, right? Okay, so what about though if we want to include negative numbers in our pile of things? We can still only encode either 256 or 4 billion or whatever the number is, okay? But we have to sort of decide how are we going to split this between the negatives and the positives, okay? And with the 8-bit scheme, the convention is that we'll sort of split it in half and we'll go minus 128 all the way up through 127. Okay, now why does it feel like 127 shouldn't be 127? Is that is that 256 things? Minus 128 to 127? Including zero, yeah. So, and that's why it's 127 instead of 128, because we need to include zero in there. That's useful, okay? Okay, so if we do this with the 32-bit scheme, it's the same idea. Okay, so what was the 4 billion whatever that we computed, right? Okay, so if we split that and say we'll do half positive, half negative, then it's going to go from minus 2 point whatever billion up through zero, up through 2 point whatever billion, okay, whatever that number is, okay? And in fact, that number is precisely, let's compute it, it's 2 to the 32nd, or sorry, 2 to the 31st. And the reason it's to the 31st is because we're spending half of our stuff on positives and half on negatives, minus 1, okay? Because we have to encode 0, and so we only get up to whatever this number is. Once the website loads, good old nice and slow. Okay, 2,147,483,647. Okay, that would be the largest number that you can encode as a signed number in 32 bits. Okay, unsigned it would be the 4 point whatever billion, basically just double that. Okay, this number is really special and interesting because this number is the number that broke YouTube. It broke YouTube, like hardcore broke YouTube. All right, so what do you guys think the most popular video on YouTube is? Huh? Sorry, I can't hear you guys. What? Charlie something? Oh, yeah. Any other guesses? Baby by Justin Bieber. Why are you two listening to that? Oh, okay. Okay. That's nice and meta, but okay. I'll dig it. You know, next thing I know, you're going to come in and be like, yeah, I was listening to what's like a girl boy band. Uh, oh, well, huh. All bets are off when it comes to J-pop and K-pop. Yeah. So, okay. Anyway, no, the video that broke YouTube was this one. Okay. The Gangnam Style music video, right? Okay. So you guys have all you guys have probably all seen that, right? You know, hey, sexy lady with the whole, right? I'll refrain from trying to do any of the rest of it. Okay. So this video at one point broke YouTube. And the reason it broke YouTube is because it actually hit that 2 billion play count number. Okay. And YouTube in the background was encoding its play counts with 32-bit signed integers. Okay, so the biggest number that they could encode would be the 2 billion number that we just computed. Well, that was all fine and dandy until this video came along. Okay, and then what happened is it rolled over and it appeared that they had a negative 2 point whatever billion play count. okay? And that totally screwed everything up. So YouTube said, okay, screw this. We're going to do 64-bit signed integers, okay? And just to put in perspective, what happens if we double the number of bits, okay? So I'm going to change this to not 31, but 63, right? So if I use 64 bits, and I'm, of course, using half of my numbers for the negatives, then this is the largest number that I can encode in that system. It's a lot bigger, right? Yeah, 9 quintillion. Okay, so get busy watching the video because let's break YouTube again. No, that's a lot of sexy lady, right? Um, okay, and just to put this in perspective, okay, how big this number is. Basically, every person on the planet would have to watch the video 1 billion times, okay, in order to make this thing roll over again. Yeah, kind of crazy. Okay, so that's sort of the funny introduction to this. Okay, now we have to get into the technical stuff. And to kind of motivate this, let me start by showing you guys a magic trick. Okay, I'm not just a mathematician, but I'm also a math magician. Okay, so let's take two amusing numbers. All right, so I'm gonna come over here and we'll do, well, actually, I'll do it here. And let me blow up the font so that you guys can see a little bit better. Let's do like 20. Okay. All right, is that big enough to see pretty nicely? Yeah, okay. All right, so, oops, let me do, oops, I want to put the 6 here and the 9 here and the 4 here. Well, actually, let me leave some space. I'll do the 6 here and the 9 here and a 4. There are the 2 there. And then I'm going to put like a, I'm thinking of this as like an answer bar, okay? So what operations could we do with these two numbers? Well, we can add them, subtract them, multiply, divide, whatever, okay? Now, we talked a lot about addition last time, and in order to talk about subtraction, right, what we're really talking is how do you deal with negative numbers, okay? So if I were to do this sort of old school, like we're back in 2nd grade, right? Oops. How would I do 69 minus 42? 9 minus 2 is 7. 6 minus 4 is 2. Okay, that was easy, right? Well, let me just change it here, and let's do instead, we'll do 62 and 49, okay? What happens this time? 2 minus 9, what do you got to do? You got to borrow from the previous position, right? So this 6 becomes a 5, and this 2 becomes a 12. 12 minus 9 is 3. 5 minus 4 is 1, okay? So we get 13. All right, does that make sense? Yeah? All right, so let me show you the magic way to do this. And this is going to blow y'all's minds. All right, so let's go back to 69 and 42, and we got, of course, 27. Okay, so I'm going to come over here, and I'm going to leave 6 and 9 alone. Okay, they're the positive number. The 42 is the one I'm going to do something with. Okay, and what I'm going to do is I'm going to sort of take each digit, the 4 and the 2, and I'm going to mirror them. Okay, and what I mean by that is I'm going to pair up all of the digits. Okay, so I'm going to pair 0 with 9, 1 with 8, 2 with 7, 3 with 6, 4 with 5, and then 5 with 4, and so on. It's symmetric. Okay, so What is the mirror of 2 under this scheme? 0 went with 9, 1 with 8, 2 with 7. Okay? Okay, so 4, 2. I'm going to switch the 2 to a 7. And then what's the 4 going to mirror to? 5. Okay? All right, I'm going to add 1 to that, and I'm going to make it 58. Okay? So I'm going to put 5, 8 here. And instead of subtracting, I'm going to add. What's 9 plus 8? Okay, carry a 1. What's 6 plus 1 plus 5? 12, carry a 1. Throw away that last carry. Okay, because if I'm thinking about this the same way that I did on the computer, okay, that if I limit myself to only using 2 digits, okay, what would happen to that 1? It would just disappear. And look what we got. Wow, that's exactly the answer. You guys like my magic trick? No? How many of you guys think I cherry picked the numbers to make this work? Yeah? Okay, fine. You pick the numbers this time. And let's just, for the sake of demonstration, in fact, you can even pick how many digits. Doesn't even have to be 2 digits. 732. Okay. And what's our other number? Which way are we doing it? The big one minus the 2,000. All right, so what I'm going to do is I'm going to write this as 0732, and what was the other one? 2,300. What'd you say? 31. Okay. All right, so let's do this subtraction problem. Okay. So which number am I subtracting here? The 732. Okay. And so the first thing I need to do is I need to do the mirroring. All right, so what's the mirror of the 0? Well, hold on, we got to do the 0 also. What's the mirror of the 0? 9. What's the mirror of the 7? 2, 6, 7. Okay. And then what do I need to do to this? I need to add 1. Okay. Oops. So 9268 is sort of my magic number. Okay, so let's come over and let's do 2, 3, 3, 1, and we'll do 9, 2, 6, 8, and we're going to add them. Okay, so what do I get? 8 and 1 is, 3 and 6 is, 3 and 2 is, 2 and 9 is 11, but I'm going to throw away the 1 that would carry to the next position. Okay, is that the correct answer? Come on, this isn't rocket science, right? Shrugs your shoulders, right? Because 2,331 minus 732, you have to do a little bit of borrowing and carrying, right? But is that correct? Yeah. Wow. I mean, you guys still think this is magic. Where did I learn this from? Well, okay. Actually, I never learned this trick in school. Okay. The way I learned this trick was actually from computer science. Okay. Because this is how we're going to deal with negative numbers in the computer world. Okay. And so what I did was I know how it works in binary, and then I just sort of extrapolated to how it would work in base 10. So, yeah. This is where the being a mathematician part is kind of handy, that knowing the trick in one base and being a mathematician means you can figure it out in the others, right? It's really not rocket science, because all you're going to do is mirror the bits or mirror the digits like we did, and then the add 1 trick is kind of yeah. I promise I'm not just pulling this. I mean, he picked the numbers, right? So you can't say that I'm fooling you here. Maybe I should go on Penn and Teller, right? That show that they've got, like Fool Us or whatever. And you guys think that they buy? No? Okay. Whatever. Okay, so this idea is exactly what we're going to do in the binary sense, okay? And what we've done here, this mirroring business is called the nines complement, okay, because we sort of flipped everything. And then if I add 1 to that number, I get what's called the tens complement. Okay, that's just the name for it. So we want to do the exact same thing, but we want to do this in binary. Okay, and the real way to think about this is, okay, that did I ever actually do subtraction here? Not really. What I did was I added a negative. Okay, now that may seem like a really subtle distinction, especially for 8 in the morning. Okay, but that's what I did, right? Instead of subtracting, I added a negative. Okay? All right, so let's do this binary style. All right, so let's go back and pray tell, what was our encoding for 69 last time in binary? So this was what in hex and what in binary? What was it in hex from last class? S'il vous plaît. Okay, hold on. Let me get over there. All right, it was what? Okay. Okay. Does that look like what everybody else had? Okay. All right. What about in hex? 45. Okay, or 4 5 really. Okay. So there's that number. And let's just take the number 5 for sake of simplicity here for my first demonstration. Okay, and what would this be in binary? 0, 0, 0, 0, 0, 1, 0, 1. Okay. Okay, does that look okay? All right, so what I want to do is I want to represent here -5. Okay, now let's take the representation for 5, okay, which is that. One way that we could do this is we could say, okay, the far left bit I'm just going to use to indicate whether the number is positive or negative. Okay, wouldn't that be a perfectly logical thing to do? Okay, if I did that though, so here's the problem with doing that. What would the bit pattern with 1 followed by all zeros represent if I did that? If I said the far left bit is going to be a sign bit rather than a number, representing a number. Well, what would the all zeros, like all 8 zeros, represent? So a bunch of zeros. What would that represent? What else would it represent, right? Okay, so Robert's like 0. Yeah, of course. All zeros, what do you think that should represent? Huh? Well, just the number 0, right? Is that okay? Okay. So if I say I'm going to use the very first bit just to indicate if the number is positive or negative. So I have 1 followed by 7 zeros. What does that represent then? What does that mean? -0? What? Does that make any sense? Okay. So that's not how we're going to do it. Okay. Because what the heck is -0? What does that mean? It's kind of nonsense, right? Okay. So that's not how we're going to do it. And we're going to use this more complicated scheme, which is called 2's complement. Why 2? Because we're doing everything in binary. Yes? Okay. So let's take this number 5 here. Okay. And in binary, my magic trick is actually a lot easier to do than in base 10 because how many different, like each bit can be either a 0 or a 1, and that's it, right? When I did this in base 10, how many different things could each digit be? Yeah, 10 different things, the digits 0 through 9, okay? So when I paired everything up, 0 went with 9, 1 with 8, and so on. Here, what's everybody paired with? Yeah, there's only one pair, okay? So this sort of mirroring procedure is super easy because all you do is flip the bits to the other thing, okay? So let's take our number 5 here, okay? And what was that? It was 0, oops, 0, 0, 0, 0, 0, 1, 0, 1. Okay, that's 5. Okay, if I flip all the bits, oops, dang it, come on, go away. I get this, right? Okay, so this is called the ones complement. Okay, where all I did was flip all the bits. Okay, then I'm going to add 1 to that, and what do I get? I get this. Oops, sorry, that. Okay, so the 2's complement is produced by flipping all the bits and then adding 1. Okay, in the same way that, remember in my magic trick before, what did I do? I flipped all the digits and then I added 1. Okay, good. Okay, so I'll let you guys scribble that down while I take another sip of my old jitter liquid. Who consumes jitter liquid? You guys ever heard this called jitter liquid? No? Has anybody ever read the comics? They go around on Facebook and stuff called Strange Planet, and it's sort of about these aliens that live on a planet, and they look suspiciously like humans, but then they do things that are kind of weird, or they use different weird words to describe what's a normal human activity. So in that world, this is jitter liquid. Okay, so we got the 2's complement of the number 5. Okay, how did we produce that? How did I get that number or that series of bits? See, oh, and this is the thing called check for understanding. Yeah. Yes. Ah, okay, good question. So I added 1 to the number, okay? And in this case, because what was the final bit position of the 1's complement? 0, okay? I'm literally adding the number 1, right? So like, let's scroll back up when I did this in, oops, here. So this digit right here was a 7. If I add 1 to it, I get 8. Let's say that that digit had been a 9. I would have added 1 and I would have had some carrying going on. I didn't in this case, okay? But I only add 1 and then just do whatever the arithmetic demands, okay? So that's the trick, right? Flip all the bits and add 1. Okay, good? All right, so let's do the computation of 69 minus 5. What should we get? Of course, we ought to get 64, okay? So if we subtract these two things, I had better get that, and that. Okay, do we agree that that's what the answer ought to be? Okay, well, let's make sure that it is. Okay, so rather than subtracting 5, I'm going to take, so let me take my, what was it, 69, okay? And let's write this out in binary. It was 0, 1, 0, 0, 0, 1, 0, 1. Okay, so this is 69. And then this negative 5, oops, freaking, just let me type a minus, please, thank you. Okay, so what was this other number that I got? This one, 1, 1, 1, 1, 1, 0, 1, 1. Oh, I can't count. Yeah, there we go. There we go. Okay, so I've got the number 69 and the number negative 5. Okay, so doing 69 minus 5 is the same as doing 69 plus negative 5. Yes, by that, right? Okay, so what we're doing, right, is turning subtraction really into addition. Okay, okay, so now we just need to add these two numbers. Okay, and this is where it's going to get a little fun because 1 and 1 is 0, carry a 1. What is going to go here? 0, carry a 1, 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 1, carry a 1, 0, carry a 1, 1. Okay, now what happens to that 1? It just disappears. Why? We're out of bits, right? 8 shall be the number of the bits, and the number of the bits shall be 8. Okay, we've run out of bits. Okay, so what's our final answer then? It's what's there, but without the one that's sort of highlighted in the box. Okay, so that we only have an 8-bit number. Yes? Is that the number we were expecting to get? It is. McKinney's wizardry strikes again. Yeah? How many of you guys are blown away by this? Yeah? I mean, it's not rocket science. Come on. Yeah? A little bit blown away? Yeah. I was going to say, and Min and Robert, you guys shouldn't be complaining too much because, well, even if it is rocket science, can you handle that? Yeah. So I'm actually teaching a course on rocket science. It's my freshman tutorial this year. So, yeah. Okay. So, you guys think I'm pulling it out of thin air? Let's pick some different numbers. Okay. And now you guys are gonna do it, and I'm gonna be the idiot up at the computer. All right. Well, how do I, here's a good question. How do you know that I haven't lied to you that this number represents negative 5? What would be a good way to verify that I'm not bullshitting you here? What would happen if I added 5 and negative 5? I should get 0, right? Yeah? Well, let's double check that we do. Yeah.
Is that including the one you added?
The hidden 1, yes. Okay, so this is why we have two different, we call 1's complement when you just flip all the bits, and 2's complement when you do that and then add 1. Does that make sense? Okay, so yeah, 2's complement means flip all the bits and then add 1. Yeah? Oh, okay. Yeah, that's not what I mean. If I wanted to do 5 minus 5, I do 5, no, I'd use the 2's complement. Basically, you only ever use the 1's complement to get to the 2's complement, okay? So if I wanted to do 5 minus 5, I would do 5 plus negative 5, okay? And so the first thing I have to do is figure out what is minus 5. How do I represent that? Okay, now in this case, we already know because we just did it, okay? So what should happen if I add 5 and this number that's negative 5? I should get 0, right? Well, let's double check that we do, because if we don't get 0, we have a problem, right? That means that McKinney done screwed up. Okay, so what's 5? Well, we already did that. 0, 0, 0, 0, 0, 0, 1, a 4, no 2's, and a 1. Okay, good. All right, what did we say negative 5 was? this. Okay, so this was minus 5. Oops, minus, dang it. Sorry. It's too early for Excel. Okay, and I'm going to add these two numbers. Okay, so what am I going to get here? 1 and 1 is 0, carry a 1, 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 and then that final 1 disappears. Okay, and is that 0? Yes. Okay, because this arithmetic system would be kind of useless if 5 minus 5 didn't give us 0, right? We'd have some major problems. Okay, so this is sort of a bullshit check just to make sure that we're doing things correctly. Okay, so let's kind of recap here then, right? So somebody give me another number, and give me a number that's between 0 and 128, or 127, I guess. Okay, 79. Okay, let's figure out how we would represent negative 79. Okay, in order to do that, we first need to know what's the representation of 79. Okay, we haven't computed that yet, so let's figure it out. All right, so 79 is the number that was chosen. Oops. Okay, so let's figure out what this number is in hex and in binary. Okay, so what is it in, well, here, let me scoot over a little bit for the binary part. 1, 2, 4, 8, 16, 32, 64, and I'm going to put an X there. Okay, why am I going to put an X where the 128s normally would go? Okay, what numbers can I encode if I'm going to include negatives here? I can go, so on the positive side, what can I do? I can go up from 0 all the way to 127, okay? I can't do 128 or bigger because I'm spending those encodings on the negatives, okay? That's why I put an X in that position, okay, just to remind us that if you had picked 203, I cannot encode 203 as an 8-bit signed number, okay? I can as an 8-bit unsigned number because then I can go 0 up to 255, but we're doing signed, not unsigned, okay? And we'll practice a bunch more of this on Wednesday, because yeah. Okay, so all right, so 79. Does 64 go into it? Yes, once, with how much left over? 15. Okay, does 32 go into 15? No. Oops. Does 16 go into 15? Does 8 once with how much left over? Does 4 go into 7? Once with how much left over? Does 2 go into 3? Once with how much left over? 1. Okay, so that is 79. Okay, and so I'll put a 0 here in this first, well, I will try to put a 0 there. Okay, so 79, what is this in binary? Well, we just said it was 1 0, or sorry, 0 1 0 0 1 1 1 1. Okay, what is that in hexadecimal? Okay, remember how do we put things into hex? We take it 4 at a time. So it's the far right. All those ones gives me an F, okay, and then the 0 1 0 0 at the front gives me a 4, okay, so in hex this is 4F, okay, and let me capitalize the F so it's easier to see. Okay, good. All right, so now that we figured out the representation of 79, let's figure out what the representation of negative 79 is. Okay? All right, so what am I going to do? All right, so 79 we said was what? 0, 1, 0, 0, 1, 1, 1, 1. So this was 79. Oops. Okay, so flip all the bits. What does that give me? 1, 0, 1, 1. Okay, and what do we call this? The ones complement. Okay? And then I'm going to add 1 to this number, and that gives me, oops. Right, okay, so that gives me this. This is the 2's complement, and this represents negative 79. Well, negative 79. Okay, so that number is minus 79. Okay, good? All right, so here's sort of one of the other kind of issues. Let's say that I handed you this number, the one that we ended up getting at the end that represents minus 79. Okay, what about if I said, well, what does this number represent? Now we know, what does it represent? Negative 79, right? That's how we got this in the first place, okay? But let's say that you had walked in the door and I handed you this number, but I didn't tell you where it came from. How would you figure out what it represents? Okay, we already know it's minus 79, but let's pretend we didn't know that. Almost. Oh, okay. You could, and get a number that you know, and then if you know your arithmetic, you could kind of work backwards to figure it out. The easiest way is, what would happen if I took a number and I computed the 2's complement of its 2's complement? So I did this sort of magic trick twice. What do you think should happen? I should get the exact same number back. Okay, now that makes sense, right? Because if I think about this 2's complement procedure is tantamount to taking the negative of the number. What's the negative of a negative? Just the regular number back, okay? So if I have this number, and can we tell just by looking at it that it must represent a negative number? How can I know instantly looking at this that it must represent a negative if I'm using the signed system? Keep talking. Yeah, the first bit is a 1, okay? All of the positive numbers have a 0 there, okay? Because what's the biggest positive number we could represent? 127, and those all have a 0 in that far left bit position, okay? So I know instantly looking at this that I've got a negative number in front of me in the signed system, okay? And so what about if I took that number, this number here, that we think is 79, and I flip all of its bits and I add 1. What do I get when I do that? Well, let's do it. Flip all of its bits. Okay, add 1. What do I get? 0, 1, 0, 0, 1, 1, 1, 1. Does that look familiar? Yeah, that's 79. Okay. All right, so here's my game plan for Wednesday. Wednesday, we're going to do basically a bunch of in-class exercises, so we won't be streaming a shitload of problems and a shitload of chalkboards. So come ready to work on Wednesday, and I'll be cracking the whip in the background. Okay? Because this takes some practice. You guys will get used to it, but um, but it does take some practice. All right, see you guys later.